All right, let's shake things up a little bit. So let's suppose we start out with only water in a rigid container, and it's a gaseous water, not pure liquid, and it's at 25 degrees Celsius. And its initial partial pressure is found to be 0.784. So we have 0.784 atmospheres of water inside of a container. What are the partial pressures of each of the species when the system reaches equilibrium? And the reaction that we're talking about in this case is water turning into H2 and O2. And the Kp for this reaction is known to be 2.0 times 10 to the negative 42. And from that value, which is extremely small, much less than 1, we can predict then that the concentration of H2O is going to be favored. So it's going to be mostly reactants. Very little of it actually goes towards the products. So what we want to do in this case isn't calculate the Kp, we want to figure out what the concentration of those two guys are right there. So we're going to wind up having to use the equilibrium equation for this. And so just keeping in mind that the Kp for this reaction, we know its value, but it's going to be the pressure of H2 squared times the pressure of O2 divided by the pressure of H2O, also squared. Now the key word here is the initial that we see right there. So this pressure that we have, the 0.784, that is not the pressure of water at equilibrium. Instead, that's the pressure of water before it goes to equilibrium. So it's the starting point. What we're saying is right now we have 0.784 pressure of water and no H2O and no O2. So we can't really do any calculations yet at equilibrium. Enter the ice table. So the ice table is what we use to figure out what the pressures or what the concentrations would be at equilibrium. And so to do that, we have to first look at the initial concentrations or pressures in this case. And so the first part's already filled out for us. The initial pressure of water was 0.784. That was given to us in the question. And since there was no H2O or O2, that means the pressure of both of those would be 0. They're going to contribute nothing to the pressure of the system. Now when this moves towards equilibrium, that means the reactants are going to slowly start turning into the products, which means the water is going to start turning into H2 and O2. So as that happens, let's start with the oxygen. So the oxygen then is going to have to increase. And the H2 is also going to increase. And in order for those two to increase, that means the H2O is going to have to decrease. And so we'll put a minus and then pluses there just to represent that. Now we don't know how much the water is going to decrease by. We also don't know how much the H2 and O2 are going to increase by. But we can look at the ratios. So if we look here, we can see that for every 2 H2Os, we produce 2 H2s and 1 O2, which means it's going to be possible to figure out what the changes are based on a variable. And so we'll just call it X. So we have some unknown amount, X, that things are going to change by. And so the O2s, there's one of those, so that means it's going to increase by X amount. Now the H2s, there's 2 of those for every one of the O2s, which means they're going to increase by 2X. So we'll get twice as much H2s as we do O2s. And then in order for those two to produce, we're going to have to get rid of some of our H2Os, which means we'll have to decrease by 2X because of 2 H2O. So what that means then is at equilibrium, we would have 0.784 minus 2x atmospheres of water. We would have 2x atmospheres of H2 and x atmospheres of oxygen. Now we can take those values and we can combine them with the values or with our Kp equation that we wrote in the first slide. So we've got our equations. Now we take the numbers from our ice table. And so, for example, the pressure of H2 we found to be 2x at equilibrium. And so we take 2x and we would square it. And we multiply that by x for the oxygen and divide it by the pressure of H2O, which would have been 0.784 minus 2x. And of course, since that's water, it's going to be squared. And we were also given the value of the Kp, and so it's going to be 2.0 times 10 to the negative 42 at this particular temperature. Now that's important because if we look at this bottom part, if we try and solve this as is, we're going to have to wind up having to use the quadratic formula, which isn't always a good time. But we can do a little test here. So what we can do to figure out whether or not this down here actually matters is if we take this value right here, okay, so the 0.784, and we subtract it from 2, and then instead of x, let's plug our Kp value in. So let's take this number right here and plug it in for x. So 2 times 2.0 times 10 to the negative 42. If you do that in your calculator real quick, you're going to come up with 0.784. Yeah, and that's because this number right here is 2 with 41 zeros in front of it. So 0.784 minus 2 with 41 zeros in front of it is still going to be 0.784. That means this number right here, this minus 2x, isn't going to play a big role. It's not going to affect the 0.784, so we can ignore it. And that's going to make our lives a lot simpler. So now just rewrite it. This is what we're left with. So we can go ahead and solve this then for x. And when we do that, and I'll let you do that on your own, we find out that x is equal to 6.7 times 10 to the negative 15. And that's why we could leave out that minus 2x, because look at that, that's an extremely small number. So we've still got to finish up by putting those numbers in. So this is the value for our x. And the concentration, that should say pressures of H2, O2, and H2O. Would be these values right here. And so another thing we can tell from this then, remember Kp, this is an extremely small number, and so since Kp is very, very less than 1, that means our reaction is going to lie mostly towards the product side, so it's going to lie to the left. And that's obvious by these numbers right there. We see we have a significant more of our reactants than we do our products. So that's the ice table. So anytime that we're given initial pressures and asked to find the equilibrium pressures or concentrations for that matter, we're more than likely going to have to use an ice table. So just be prepared to use them. They're not going to tell you in the question, hey, you need to use an ice table here, but add them to your arsenal. Be ready to use them.